Welcome to homework set number 9 for ECE 320. This homework set looks at Mosfet switches and Cmos logic. The first problem is, given this Mosfet, determine K sub n, label the regions. The regions are this. You've got a parabola, that's the ohmic region, right at the origin. As you change the voltage, I change the slope, that's your resistance. As I increase the voltage, VDS, I get more and more current. And then I start running out of electrons or charge carriers, and the current becomes constant. So this part over here, the separation between the curved region and the flat region, the one on the right is saturated. I've run out of charge carriers, hence the name saturated. On the left is ohmic, and the x-axis is off. To find the parameter K sub n, pick a point. Doesn't really matter which point you pick. I picked 7 volts to 90 milliamps, so picked a point right here. When VGS is 7 volts, slide that up some, VGS is 7 volts, I'm getting 280 milliamps, and that's in the saturated region. So use the equation in the saturated region, that's this guy. Plug in numbers, I got 290 milliamps. The threshold is given as 1 volt. At 7 volts, solve for K sub n, I get 0.0161 amps per volt squared. The threshold voltage you can find as the voltage VGS gets smaller and smaller, down here. The current gets less and less, so the threshold voltage is less than 2. How much less, you're not really sure, but just because I did the graph, I know it's 1 volt. That's one way to do it. Second way is you could also pick a point in the ohmic region over here. If you do that, just make sure you use the correct equation, the equation in the ohmic region, and you'll get the same answer. Problem 2 says draw the load line and find the operating point when the gate voltage is 0, 4, and 7 volts. So for the load line, the x-intercept is at 10 volts. That's up here. When the current is 0, I'll have 10 volts across it, down in the lower left corner. Curse. Fighting with my display here. There we go. 10 volts lower right corner. On the y-axis, 10 volts over 40 ohms is 250 milliamps. So VDS is 0 volts. I'm right here at 250 milliamps. 2 points determines a line. Draw a straight line. That's shown in orange. When the gate voltage is 0, I'm off. That's right here. When the gate voltage is 4 volts, I follow the 4 volt line, and we'll see where it intersects. And that'll be in the saturated region. At the 7 volt line, I see where it intersects, and that's right here. That's in the ohmic region. For a Mosfet switch, MOSFETs are actually really easy to use as switches. You just basically place the N-channel MOSFET between your device and ground. If VG is 0 volts, it's turned off. If it's something like 10 volts, it'll be roughly 0.008 ohms. Basically a switch. So first, one way to do it is just assume 0 ohms off, actually infinity ohms off, open circuit, 0.008 ohms on. Another way is slightly more accurate. Calculate K sub n. From the specs, I can tell you what K sub n is. It's 0.008 ohms, which tells me I'm in the ohmic region. So use the ohmic equation. I times R is voltage. VDS is 0.496 volts, so that plugs in right here. VGS is 10 volts. The threshold voltage is given as 4, in worst case. That's at 62 amps. Solving, I can tell you what K sub n is. And this is a IRF 3205 MOSFET from DigiKey. Complete overkill, handle 110 amps. We can't do 110 amps in lab, but the MOSFET could. Repeating what we did before, if I have 0 volts and 5 volts, calculate the voltages. 0 volts is pretty clear. It's off. 0 is less than 4 volts. There's no channel, no current. When Vn is 5 volts, I'm not really sure which region it is. Let's guess the saturated region, because that equation is easier. If I assume it's saturated, I'm at 5 volts, the threshold is 4 volts, there's K sub n, calculate IDS, I get 10 amps. VDS is then 10 minus I times R, negative 76 volts. So on the load line, I'm way over here at minus 76 volts. That can't happen. I can't have a negative voltage, because if I did, it would produce energy. What that tells you is my assumption was wrong. It is not saturated. So let's try the ohmic region. In the ohmic region, I have two equations, two unknowns. Here's one of them. That's the equation in the ohmic region. I've got the load line. For your circuit, 10 volts is IDS times 8 plus VDS. Solving two equations, two unknowns. The answer I want is the one close to 0. Its VDS is 0.0589 volts, and IDS is 1.24 amps. If you're curious, the resistance is voltage over current. This isn't actually 0.008 ohms, it's actually 0.04 ohms. If you want to split hairs, not a huge difference. If Vn is 10 volts, this is going to be the ohmic region as well. I've got two equations, two unknowns, solve. And what I do is I just iterate. I've got, actually on the load lines, come on puppy dog, I get this, that equation is a parabola. The second one is your load line. I'm going to guess the voltage, VDS, find the first answer, find the second one. I want the difference to be 0. Keep on iterating until the difference is 0. That's my function equals 0. I've got function equals 0 programmed on my calculator, and I'll just iterate until it finds the 0. The 0 is the one closest to the y-axis, the small VDS. Turns out VDS is actually 0.0096 volts, and the resistance is 0.0077 ohms. IDS 1.24 amps. Problem 5 is simulate in Circuit Lab. When I have the input of 0 volts, I have 0 amps, not surprising. At 5 volts, I'm getting 64 millivolts VDS. At 10 volts, I'm getting 14 millivolts VDS. So comparing the calculations versus simulation, they're close. The VDS, a little bit different. Again, Circuit Lab uses a slightly different model. I had to change the parameters to match what we calculated. So the threshold voltage is 4 volts. K sub n was, whatever it was, 21.73. And even then, the answer was a little bit different. If I build it in lab, again, I'll get a slightly different answer. But from a practical standpoint, I'm getting darn close to 0 volts. This is part of the reason that MOSFETs are better than BJT transistors. For BJT, the saturation voltage is about 0.2 volts, ballpark. For this MOSFET, when it's turned on, I'm getting 14 millivolts. Much, much smaller. So they can also handle much higher currents. The last problem is Cmos Logic. Come up with a gate to implement this logic using Cmos Logic. And you can circle the 1s or circle the 0s. Either one works. I personally prefer circling the 0s. What that'll do is that'll give you the logic for the low side of the Cmos logic. When the low side turns on, it's pulled to ground, or 0 volts. So my preference is circle the 0s, and that gives me this logic. The red line is A bar, B, C bar. The blue, A bar, B, D. The green, A, C, D bar. Using Demorgan's theorem, I get Y logic. Y bar is implemented on the low side. So here's your Y bar. I'm going to be pulled low if I have A bar, B, C bar is true, and this path gets turned on. If A bar, B, D is true, this path gets turned on, and ACD bar is true, that path gets turned on. So that's Y bar being pulled low. For Y, use Demorgan's law. Series becomes parallel, so the blue line becomes this guy. The red, series becomes parallel. Purple, series becomes parallel. Parallel becomes series, so each of those is cascaded. That's the high side. And the A bar stays the same. That's due to a double negative. For Demorgan's law, A bar goes to A, but for p-channel MOSFETs, these are p-channel, these are n-channel. For p-channel MOSFETs, 0 volts is on, 5 volts is off, so I get a double negative. So A bar stays A bar. And the neat thing about the MOSFETs is I can implement the entire logic in one circuit. I don't have to do ands and ors and nands and stuff like that. Do it all at once.